Okay. So, indeterminate forms are limits that we cannot just evaluate using our other tools. So, things that we can't just plug in and evaluate, we can't just multiply by a conjugate, or anything like that. So, remember, our goal with these is ultimately to apply L'Hopital's rule. And L'Hopital's rule says you can do the derivative of the top over the derivative of the bottom and evaluate that limit, and it will be equivalent. Now, thing to be cautious of there, we're not doing the quotient rule, which is slightly confusing. We're used to seeing a fraction, doing quotient rule, and we still have to be able to do quotient rule, but L'Hopital's is doing numerator and denominator separately than their equivalent. So our indeterminate forms that we have seen. The first day we did our straightforward ones. If it's 0 over 0, or infinity over infinity. Those are the two that we are able to go straight into L'Hopital's. So any of our other indeterminate forms that we encounter, our goal is going to be to try to write them in this form so that we can use L'Hopital's rule. All right, then after that, we talked about the indeterminate product, 0 times infinity. We can't just look at that and know what it is. We know a number times 0 is 0, a number times infinity is infinity. When you put them together, it kind of depends on which one's getting there faster, or do they meet in the middle somewhere. So we can't just evaluate it. What was our strategy on those problems? Not on that one.
Oh, is that where you have to get that?
Yes. We have to turn this into a fraction. So we divide by the reciprocal of one of them. So that's written as a fraction. And then you can do L'Hopital's from there. Okay, the next indeterminate form we had was infinity minus infinity. So, our goal is to get a fraction. If you are adding or subtracting, how do you get that into a fraction? That's what you were saying.
Oh, this one you did go on?
Yeah. Common denominator, and from there we can do both sides. Then we got into our final type, which was the indeterminate powers. So our powers, if we have 0 to the 0 power. Okay, the reason that's indeterminate, 0 to any power is 0, but anything to the 0 power is 1. So it's like a race. Are we getting to the 0 or are we getting to the 1 or something in between? The next one is infinity to the 0 power. Because again, infinity to a power should be getting bigger and bigger, or smaller and smaller if it's a negative power. But anything to the 0 becomes 1. So we can't just look at that and know. Do you remember what the third one was? 1 to the infinity. Because 1 to any power is supposed to be 1, but anything to the infinity power is getting bigger and bigger. And so it depends, are we getting to the 1 faster or are we getting to the infinity faster? So these are the indeterminate powers. Do you remember what our strategy was for those?
Natural law.
We add a natural log. We write it as a quotient. And we can do L'Hopital's. And then how do we answer?
Take your answer to the power of e.
Yes. So the answer will be E. All right, so those are the indeterminate forms. In all of them, the goal is to ultimately use L'Hopital, so we have to do algebra techniques to get it so that it's 0 over 0 or infinity over infinity, and then we can do L'Hopital. When we did it last week and we were doing one piece per day, then we had it broken up. So what I'm doing today is just giving you one that has everything mixed together, okay? I do want to take a look at the very first question together, though. So the very first question. And we have to be a little bit careful here because exponents only apply to what's directly in front of them. So the thing about this one, only the x is being raised to the power. So we could just take that 4 out in front of the limit. Okay. So if I'm trying to evaluate this, if I'm plugging in, that's infinity. 1 over infinity goes to 0. Infinity to the 0, that's one of our indeterminate forms. With the powers, what was our strategy? Add a natural log. Okay, the 4 that we took out just stays. Okay, I'm adding my natural log here. And the reason we add that natural log is properties of logs. What happens to the exponent? Okay, and our goal is to get this written as a fraction, which is really easy to do because if you take 1 over x times the natural log of x, you just get natural log x over x. So now we have a fraction. If we plug in the natural log of infinity, remember our natural log graph looks like this. So as it's going to infinity, it's going, you're just getting infinity over infinity. If you have infinity over infinity, what can we do? And remember I did ask that you label when you do L'Hopital, so just put LH there so I can tell this is the step where we did it. Okay, so natural log of x turns into a 1 over x over derivative of x is 1. So now if we evaluate, all right, 1 over infinity is going to 0. So 0 divided by 1 is 0. Now this one is slightly tricky, which this is the reason I'm doing it with you. We took that 4 out of the beginning. That 4 is the thing that kind of changes this. Typically at the end we just say e to some power, right? Well, when we added the natural log, we only added it inside the limit. So when I add my e back, it's only going with the thing on the inside. Does that make sense? So I added my natural log here, so I have to add my e here. So it's like 4 times e to the 0. Anything to the 0 power is 1. So 4 times 1 is 4. So that one just had an extra little,
So the 4's even outside the even.
yes.
Okay.
So, like, if you wanted, when you took out this 4, we could have just dropped it for now and said, okay, my answer is going to be 4 times e to some power.
Mhm.
So, basically, we just took out 4, we're going to ignore it into the end, just like when we had that natural log, so the 4 just stays out in front. Alright. Any questions there? Okay, so what I want to do is give you guys some time to work